Hello everyone, this is Amit Brambhat, your professor for CSC 208 at Laurel Ridge Community College, part of BCCS. Today we are going to go over a chapter on discrete structure for computing, which shows you how to work with sequences, sums, and products. So let's get started and let me share my screen with you. So good. Hello everyone, welcome back to this discrete structures class. We'll initiate our formal examination of sequences, sums, and products. While you may have intuitively interacted with ordered numbers in previous calculus or algebra courses, our objective today is to conceptualize these structures from a rigorous foundational computing perspective. We'll evaluate how sequences are formalized, how recurrence relations model algorithmic execution, and how algebraically manipulate summations and products to determine computational complexity. So we are going to talk about discrete ordered lists. We need to understand and unpack the architecture of discrete ordered lists. In computer science, data structures like arrays, vectors, and queues are fundamentally built on conceptual framework of mathematical sequences. To analyze this efficiently, we must first abstract them as functions. Let's talk about sequence formalism. Formally defined, a sequence is a function where the domain is a subset of integers, typically beginning at index 0 or 1, and the domain code domain is specified set S, unlike a standard continuous function. The inputs here are intrinsically discrete. When we write the notation wrapped in curly braces, we are referencing the sequence in its entirely. Individual elements within this ordered collection are designed as terms mapped uniquely to their respective indices. A sequence can be bounded and finite, or it may be infinite, possessing no upper bound. It's crucial to remember that order matters fundamentally here. A change in the index permutation yields an entirely distinct sequence. Progression archetypes. Within sequence analysis, we frequently encounter two foundational progression archetypes. The first is the geometric progression. Here, each consecutive term is generated by multiplying the preceding term by a constant factor known as the common ratio, denoted as R. This yields exponential behavior, which you will see frequently when measuring things like binary tree expansions or divide and conquer algorithm partitions. Conversely, an arithmetic progression evolves through a linear trajectory. Each subsequent term is derived by adding a fixed constant, the common difference d, to the prior term. Recognizing which archetype governs a dataset or an operation allows us to instantly deduce its long-term behavioral characteristics. Let's evaluate this mechanics dynamically using this table. If we take an initial terms of 2 and apply constant step of positive 3, we generate a predictable linear sequence. This can be expressed instantly as a closed form formula without needing to calculate all prior steps. However, look at the later rows. A sequence mapping number of letters consecutive English words. While we can easily calculate empirical values for 4, 3, 3, 5, This sequence lacks an explicit algebraic closed form because its underlying rule depends entirely on lexical semantics rather than mathematical functions. As a computer scientist, our ultimate goal is almost always to derive the closed form representation shown in the third column, as it allows for O of 1 algorithmic evaluation. Recurrence relations. Note that we can express sequences using explicit functions of an index. Let's pivot to a more dynamic paradigm. Let's investigate recurrence relations, where a term's value is explicitly bound to the states that preceded it. The Fibonacci sequence. The quintessential exemplar of a recurrence relation is the Fibonacci sequence. By definition, a recurrence relation expresses a term Fn as a function of one or more of its preceding terms. However, a recurrence relation is mathematically incomplete and unsolvable without specified initial conditions, analogous to the base cases in a recursive software function. For Fibonacci, these base parameters are f0 equals 0 and f1 is 1. This specific additive recursive structure underpins a vast array of natural phenomena and computational optimizational problems, particularly in dynamic programming. Iteration method. To transform a complex recurrence relation into a highly effective direct evaluation formula, we utilize a technique called the iteration method. We can approach this from two directions. Forward iteration begins at the foundational base cases, building upward systematically until a recognizable inductive pattern manifests. Backward iteration or backward substitution works inversely. We take the generic expression for A of n, substitute the definition for A of n minus 1, expand it further to A of n minus 2, and unravel the math backward until we reach our initial constraints. Both pathways aim for the exact same milestone, eliminating recurrence altogether to establish deterministic closed form formula. Sum of consecutive integers. When evaluating loops in algorithm analysis, we inevitably must sum the terms of a sequence. This brings us to series summation. Consider summation of the first n consecutive positive integers. Legend holds that Carl Friedrich Gauss derived this formula instantly as a child by pairing the first and last elements of the series, noticing that every pair summed identically to n plus 1. Because there are exactly n by 2 such pairs, we get the elegant identity n in brackets n plus 1 divided by 2. Whenever you encounter a nested loop structure where the inner loop decrements linearly, this is the exact mathematical mechanism you will use to calculate the total execution steps. Summation and product notation. Let's standardize our notation to prevent ambiguity. The uppercase Greek letter sigma denotes a summation, bounded by a lower limit of summation, the initial index value, and an upper limit. One of the most powerful properties of sums is linearity, meaning that any multiplicative constant independent of the index can be factored completely outside operator to simplify the arithmetic. Additionally, we introduce the multiplicative analog to sigma, the uppercase Greek letter pi. This symbol commands us to multiply a series of terms rather than add them. Understanding the distinct properties governing both operations is essential for parsing formal algorithmic specifications. Essential identities. To conclude our mathematical toolkit, we must commit these essential identities to memory. The geometric series summation is highly prevalent when calculating the total node count of balanced search trees. Note this critical caveat. This formula is strictly valid provided the common ratio R does not equal 1. Besides it, we see a foundational product identity. When scaling a product sequence by a constant, that constant is multiplied by itself for every single step of the range, transforming it into an exponential factor. Mastering these manipulations allows you to bypass laborious manual evaluations during complex proofs. So if you have any questions, feel free to reach out to me by sending me an email. My email address is abrambert@laurelridge.edu. I'm looking forward to see you in the next classes. Take care. Bye.